So let's start. Okay, so we want to prove this Zimmer cocycle super-rigidity. So I will do it in dimension 2, I hope, today. And then probably some of the lemmas the key lemmas we have to play with, I probably will state them in full generality if I can. And then we just see how this is really proving the full dimensional situation, not just the two-dimensional case. But the pictures and the whole idea is quite clear and immediate in dimension 2. Higher dimension is just a matter of complexity of, as always, higher dimensions. So let's try to do it. So let's remember what we are trying to do. So we have G acting on X. This is amenable. We preserve a measure mu. We have a cocycle. X times G or G times X into, and as I said, I will do the SL2R situation here. And then we want to find the matrix C from X to SL2R such that Cx phi of Gx, Cgx inverse is, okay, and I will already move into something which is not even true, but still. I really want to do this, to make it upper triangular. It will not be possible, and we will see what happens when we cannot do it. Okay, so what's the main idea here is that having this 0 down there means that if I take this space E of X equals to Cx of 1, 0, then this guy is preserved by my cocycle. So phi of Gx equals to, oops, apply to Ex, E of Gx. So into solving this equation, what I'm actually looking for is for this invariant bundle. Now, remember also, which is related, and that's how we are going to argue, that this expression, these upper triangular matrices, were related to this L delta at this space. Okay? So actually, what we are going to do is the following extension, X times RP1. Here it will be a RPN, but really not serious. And we make G act here by G of X E equals to Gx phi of Gx applied to E. And then what we are looking, if we want a solution to this equation, is a section. So we want E from X to RP1 such that the graph of E is G invariant. Okay, so this is what we are looking. This guy. So it will not always exist, but we are still looking for the guy. So you see, we have played this sort of game several times, and it's very natural. So in dynamics, this type of interpretation of invariant bundles, diagonalizations of cocycles, invariant graphs is always showing up. And here it shows up again. So how we look at this graph? So this graph is an invariant set, is a G invariant set for this dynamics here. Okay. So what we are going to look for is, well, we could try to look for invariant sets, actually, directly. So pick some reasonably nice invariant set with some minimality property. So this is the smallest possible, because if it is a graph, so let me draw the picture here. Here is X, here are the circles. So the graph, the whole point is that the intersection with the fiber is just a point. And so if you want to find a set doing that, you want to have some minimality, so you don't want to make it larger. So you have, of course, the invariant set, which is the whole X times RP1, and you don't want to have this. You want someone which intersects the fiber in just one point. So what one typically should do is pick a minimal set, for example. But then you have to be minimal with respect to projecting into the base. And actually, one can follow this type of argument and see wherever one can go. And this will pretty much in the line of Gottschalk-Hedlund type of proof of trivialization of a cocycle over a minimal system. So that's what the Gottschalk and Hedlund do after all. Here is a measurable system, so we argue a little bit differently. So in Gottschalk-Hedlund, the action on the fiber is isometric. Here, the action of the fiber is just by application of these matrices, which may be isometric, but most likely is not isometric. And then we have to see what we get. So that's what we are going to do. So instead of taking an invariant set, and I'm insisting on invariant set because I really would like you to think of a measure as an invariant set. And actually, it's much more than an invariant set. It's giving you much more information. So it's an invariant measure, a measure in general, is really giving you a huge amount of information on your space, on what you are looking for, on your problem. So much more than a set. So because especially in this picture, even though X may not be topological, the circles are very nice, beautiful space. So you understand your global space in a reasonable way. Then you start measuring balls in your space. And if the measure is large in this ball, it's telling you that your problem is concentrated in this ball. And you know this ball because you know the space. Okay? So if the measure is atomic here, well, here is an atom. If the measure is very small in this region, then I don't need to care much of this region. And then the measure is really telling me a lot, not just like a set. Okay? The measure could be supported on a manifold. And then really, I know pretty good what's happening with my measure. Okay, so then instead of looking to a set that intersects the fibers at points, I'm looking for a measure. A measure that projects to my invariant measure down here, of course, and a measure whose conditional measures are atoms. Just one atom. That's what I'm looking for. If I do this, then I have my graph, my E of X, my everything. So what we are looking for now is for a measure nu on RP1, oops, on X times RP1, such that 1 pi, here pi is projection into the first coordinate, because I want this guy, I want this E of x to be defined mu almost everywhere, so I want E of x to be defined mu almost everywhere, so I need the measure to project to mu. And second, again, second will be really tough to do and impossible in some situations, but yeah, I still want it. I want that mu x RP1 be an atom. Okay, and this atom I'm calling it E of x. Okay, so that's what we are looking for. And that's what. So now we can start, because the first is very easy to get. And that's why we assume the group is amenable. If the group are not amenable, this is essentially impossible. But if the group is amenable, this is very easy to get. So, lemma, there exists mu, a probability measure on x times RP1 such that nu is ergodic, G ergodic. That's ergodicity is sort of the minimality assumption I was using. It's not so serious actually. So it's G ergodic, G invariant, and pi mu equals to mu. So far, so good. Okay, so proof is just averaging. Okay, so I take this simplex, so this compact convex space, which is P mu is all the probability measures on x times RP1 such that pi nu measures mu equals to mu. And this is a compact convex set, and it's G invariant. So since G is amenable, whenever it acts on a compact affinely, whenever it acts affinely on a compact convex space, it has a fixed point. Hence, invariant set where G acts affinely, hence G has a fixed point. On P mu RP1, and finally, so let P mu G equals to all these invariant measures in this set. We just show that this is a non-empty set, and the extremal points in here are ergodic and G invariant because you take them. Then you are done. Okay, so it's a cheap proof from definitions and core theorems, quite broad and general theory. So for the number 200 million times in this course, we apply Rocklin lemma to this measure. So this integration lemma. You see, that's the reason why mathematicians are not rich. If we were working in a different sort of profession, whenever I write this amount, the thing, I should pay $1 to Rocklin. And then Rocklin would be really billionaire. And Rocklin sons and the rest of the people. So, and that happens for the other things, but for some reason mathematics, I'm free to say it and it's for free. That's so bad. Of course, then if you want to be rich, you want someone to cite you, and no one will cite you because they have to pay you. So then you really need to do something important. Well, what to do? Okay, so we apply Rocklin's integration lemma. And what we get is this map mu sub dot from x into probability measures of RP1, which is measurable, defined mu almost everywhere, and it has the invariant property, and the invariant property we care is that phi gx star mu sub x is mu sub gx. So we got something very similar to 2, actually, or very similar to the consequence of this, which was 2. So we just need to make sure the support of this measure is an atom. Okay. Now, how do we show support of mu x is 1 point? And this is actually Furstenberg brilliant idea, which is you have no clue of what is your action of G, your G action. So that's given to you. No one is telling you what it is. You just know G is amenable, but other than that, no one is ever telling you anything about it. Okay? So if you don't know, you don't use it. So, but this is a matrix acting projectively on RP1, and this is a measure on RP1. So how do matrices act on RP1? Okay? And here is how matrices act on RP1. Okay? Now, imagine A is huge, a huge matrix. Then what A would do? Well, A would take 1 point, it will not move it. It will take another point, it also will not move it. But then it will take this complement of this point, and it will map it into here. So it will really attract everything towards there. So it will collapse everything. Okay? So that is true. So one needs to prove it. But that's a truth of life. Okay? So that's how the dynamics of a matrix A looks like. Typical matrix A. Of course, the matrix A could be orthogonal. The matrix A is orthogonal, you just rotate and you do nothing. There are all sorts of examples where the matrix A does not do that. But a typical large, very large matrix is doing this. It's taking a very small guy and collapsing it to a point. So let me just write down briefly how this is true. So this matrix is, and let me write here e to the t, e to the minus t, as a typical. This is what is called the KAK decomposition, which is just yet one more instance of this polar decomposition, or the fact that every every symmetric matrix can be diagonalizable. So that's a very easy fact. And then once I have this, O is orthogonal, O1 is orthogonal, O2 is orthogonal, and this guy is, as soon as t is huge, so the norm of A is e to the t. So as soon as t is huge, this matrix here is doing exactly what I said. Okay? So it's this north-south pole map, which e to the t, actually e to the t square, collapse everything. E to the 2t, not t square, collapse everything to that direction. And then this is an orthogonal movement. Okay, even though I draw this as if it were the same, it's a little bit tilted, so I'm not even using that this is the same guy. Maybe let's put it here so we make sure. Doesn't matter where it is, it's somewhere. But that's what it does.
So you don't care that A has fixed points, really?
Yeah, I don't care at all about A having a fixed point. So actually, this point here, let's see here, t is positive, actually, very positive. Okay, then this point should be the O1 inverse of the point 0, 1. This is O1 inverse of the point 1, 0. And then this point is the O2 of 1, 0. And there is a point here, which is the O2 of 0, 1. Okay? So I take this point is mapped into the 0, 1, the 0, 1 goes to the 0, 1, O2 of 0, 1 map it here, this is A of this point, same thing with this guy, and then if I take any point here, the orthogonal map will rotate it, then the diagonal will send all the way to this 1, 0 direction, and then the second orthogonal map will rotate it again, but will not affect the distance. So that's what a matrix does.
The circle of circumference pi is the projected circle, not the actual circle.
It's an RP1. It is, you are right, so this orthogonal is acting by half the angle, or twice the angle, I never remember. Twice the angle, yeah, okay. But it's still an isometry. Because, yeah, from the R2 picture, we are really only thinking about this guy, but still this is how we are measuring angle, and this guy rotated, so there is no harm on it. And yeah, as you said, this is pi length. Okay, so what does this picture prove? Well, this picture proves the following. Lemma. Let An be a sequence of matrices such that norm of An goes to infinity. And okay, now I will do something just because I don't know how to do better. Probably one can do it better and cleaner what I'm going to do, but still, let me do it. So let Ni be a subsequence such that, actually let me not put this. This will be one of the possible outcomes. Okay, let me use a sequence such that a Ni, oops, over the norm of these matrices converge is convergent to some matrix V. Then either one B is B belongs to GLN, R is GL2R, and hence norm of An I is bounded these are equivalent essentially, or to there exists one guy which I will describe later, E naught in RP1 such that let me write things correctly, how I do want to write it, yeah, such that A Ni restricted to RP1 minus E naught converge to image of B uniformly on compact sets. Okay, and here maybe if you want there is an observation which is rank of B equals to 1. So the rank of B can be 0, 1, or 2. And if the rank were 2, we are in case 1. The rank cannot be 0 because the norm of B is 1. So rank 0 means you collapse everything. So the rank is 1. Just to make sure this image is not trivial, so I wanted to say it's a line. So here, the picture of this is I have this sequence of functions from RP1 to RP1. I restrict this sequence of functions to this complement of this E naught, and I have this sequence of functions converge uniformly to this image of B. Okay? Okay. The proof?
Any point that is not E naught converges to this.
In particular, every point that is not in E naught converges to image of B. And it does it uniformly on compact set. So whenever I take any neighborhood of E naught and I leave it out, the distance here, so here is for every, so this is for every k contained in here, so for every complement of A naught, the sup over k of with E in k of the RP1 distance of A and I of E to the image of B goes to 0. Oops, this is a capital. Okay, so that's in particular for every point, because a point is compact. So yeah, maybe I need to take, no, I took B already. Do I need to take a subsequence here? Wait a second. Wait a second, what is this? Just give me a second. Okay, maybe it's true this way, but there exists a subsequence, and the subsequence A and J, so that this is true for the subsequence. Yeah, I think it's true for the sequence, but certainly for the subsequence it will be true. And we just will need it for the subsequence. Okay, the proof of this is essentially this picture. We will go through this proof, but it's essentially this picture. Okay, so just add a subscript n here, a subscript n here, subscript n here, subscript n everywhere. Take subsequence so that this sequence of orthogonal matrices are convergent, this sequence of orthogonal matrices are convergent, and then we know exactly what is B. B will be exactly O to infinity 1, 0, 0, 0, O 1 infinity. Again, assuming the norm goes to infinity. If the norm doesn't go to infinity, there is not much to do. And then we have this sequence of points will go to what we call E naught, which is what I thought, the kernel of B. So that's why I think we don't need to take the subsequence there, because this E naught is the kernel of B. So even though notice it's not so important, here I know a little bit more than what I know from there, but I think I can get what I'm getting here from the hypothesis there without a subsequence. So I'm not taking just the subsequence here so that A is convergent. I'm taking the subsequence so that this O is convergent and this other O is convergent, which in principle would be a little bit more than asking for the sequence of AN divided by the norm to be convergent. But still, I think it should be okay. Anyway, doesn't matter because we are fine by taking subsequences. But it's just a comment. You can do the proof by yourself. And then that's it, because I know I fix a compact neighborhood outside of this guy. Then for this fixed compact neighborhood, I can take n large enough so that all these points land here, and then I just make this norm here very large so that things becomes here very close to this guy, and then I'm done. Okay, and remember, this is isometric. This really is the guy doing the game. This is isometric, so nothing changed. Actually, you could do the proof pretty much the way I do by not conjugating, by saying the O to the other side, the O to the other side, and only proving the theorem, the lemma for this sequence of matrices. And for this sequence of matrices is pretty trivial. Okay? But it's not pretty trivial, it's the Morse-Mail dynamics. So it's what you prove in Morse-Mail dynamics. Okay, so I think with that I don't need to write down proof of the lemma. You can do it by yourself. It's a nice exercise. I was going to say something more, but now I don't remember what else I was going to say. Okay, at least let me see some other thing more, which is in higher dimensions you have very similar statement. The only difference, and is quite a difference, is that here you will have diagonal matrices, but they may have similar eigenvalues. Okay, there may be non-dominant eigenvalue. You may have e to the t1 up to e to the tk, and then other ones. And all these guys dominate the other ones, but they don't really go to infinity. Then you just take subsequences and make all these guys convergent, and the outcome will be what the natural outcome. So the distance to the space generated by these directions, maybe moved by the other orthogonal matrix, goes to 0. And that's all we care. So, and that will be fine. Okay? So, so it's not really hard to get a counterpart in higher dimensions. Oh, and now I remember what I was going to say. So this phenomena I'm describing here, so the phenomena happening for this lemma, where you really go to a point, so not like here where you are going to a subspace, when you really go to a point, it's called proximality. Okay? So when these matrices do this game, you call them proximal. That was Furstenberg called them. Okay, now how we use this? Well, remember we know phi g x is nu gx. Okay, now just take any sequence gn for that matter, and consider these matrices. Okay, and imagine you know that gnx goes to y. And imagine you know on top of it that this is also true, and you know that we can do this type of assumptions by staying loose in sets of continuity and blah, blah, blah. Okay? Then, if I have all these assumptions, then what do I get? Either norm of an stays bounded, or yeah, take subsequences if I want. Okay. Sorry.
So wait, are you taking X to be a compact matrix space?
Yeah, just to do this argument, yes. Yes. But that can always be done. It's for L space, so it's the interval 0, 1. So, so now I take a subsequence, ANI goes to B, and then either 1, I get two properties, norm of and B of nu X equals to nu Y, or 2, I can take a subsequence, Nij, and have the following. Of course, this is a lemma, which is 2, I guess. If nu X of E naught is 0, or actually, let me really do the strong statement, and B star of nu X, it's not so easy because I need to do the computation correctly, minus nu X E naught delta E naught. Okay, so that's a measure, it's not a probability. So now I normalize it to keep it a probability. When I apply this to the matrix B, what I'm getting is mu of Y and divided do I have to divide it? Yes, I have to divide it. No, I shouldn't divide it. Yes, because it's not onto. Okay, yes, I get that. And it's not nu of Y, I'm sorry. Ooh. This is, yeah, I don't need to divide it. I'm getting delta at image of B. That's the whole point. I'm sorry. I'm not sure if I have to divide it.
So that lemma 2 is part of option 2?
Yes.
Okay.
And is essentially a corollary of lemma 1. So actually, let me state the lemma 2 in a better way. So let's call this lemma 2 prime. So let an and B be as in lemma 1 and assume lemma 1 condition 2. Then B star for any measure for every call it nubar probability on RP1 such that nubar of P naught is 0, B star nubar is delta at the image of P. So this uniform convergence on compact sets on the complement of E naught to the image of B is making that any probability measure supported on the complement of this E naught, so which give full measure to the complement of E naught, is mapped all the way to the image of B. Okay, and that's why, yeah, I don't need, since I wrote the normalization here, I don't need this here. So, okay.
So on the right side of this board, do you assume that up to a subsequence this an divided by its norm converges to a linear map, or are you saying that there is such a map?
We can take a subsequence. So here, actually, so this is going to be already that we already know. I'm taking a subsequence. Let ni be such that it converges. And B, so B is the limit of this convergent subsequence.
Okay.
B is really irrelevant here. What is relevant is this. Because then what am I getting? I have that this guy here is an star mu x. Because that's the invariance property. Here becomes this. And what I'm getting, there is this problem with E naught, okay? Let's forget for a second about E naught. What I'm really getting is that this guy is going here. That's what Furstenberg proximality is telling me. What is continuity telling me? That this goes to nu y. So hence nu y is delta at the image of B. Okay, so that's how it is. So this implies that this guy is atomic. Now I have to discuss, there is a set of full measure, the set of positive measure plus ergodicity, blah, 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 whether this measure is atomic or not. Okay? So if this measure is an atom, then always, then that's what I wanted. If this measure is not an atom always, then I get that these norms are uniformly bounded. And then, actually, by playing pretty much the same game, using this limit in B, I will be able to show that the measure is actually Lebesgue. No, it's not Lebesgue. It's fully supported, but once it is fully supported, it's essentially Lebesgue. Okay? So I will go here, the argument, through this classification of subgroups of SL2R, preserving a measure for its action on RP1. And that's what we are going to play here. So the only problem is that shows up is when this E naught really is messing up, and then what I will get is that the measure nu y is actually this delta in the image plus with some constant C1 plus some constant C2 and a delta on E infinity, which is infinity is a limit of the sequence of directions an of E naught. And an of E naught, even though the vectors there go to 0, as a direction, it has a limit. I take subsequences, it is convergent. And then these measures actually, in general, will converge into something like that, which is that this measure has 2 atoms, not 1. Of course, it depends on the value of C2. C1 is always positive. C2, well, it's not always, because it may be measure nu x full atomics in E naught. So, yeah. So still, this is a convex combination of 2 atoms, maybe 0 or 1, but still, this measure then has 2 atoms. And then we discuss whether you preserve 2 atoms, 1 atom, then you have upper triangular or the cross intertwined in the directions, or the norm of the matrices are bounded, the B is invertible, and maps nu x to nu y. And then still we will be in business. Okay? So we are going to do this on Wednesday. So I will rewrite on Wednesday this lemma, and I will prove lemma 2, and then show how this implies. Okay, thank you. Good. Okay. Let's start. Okay. We were in this Furstenberg lemma and this game we were doing. So let me just remind you a little bit of the status of what we were doing. So we had G acting on the space X. We have a cocycle taking values in SL2R. So far, here we preserve a measure mu. We look at this cocycle dynamics, X times RP1, and we make the guy act here, and we found a measure mu here that projects into X mu, and G act here. So we have this projection into the first coordinate, and the y G acts at XL is Gx, and we do phi Gx of L. So that's how we act on this RP1 on the space of lines. And we have these measures. So these probability measures so this measurable function which satisfy that nu Gx is phi Gx star nu x. So that's the invariance. This measure nu, so mu is ergodic, and nu is also ergodic. What else? I think that's it. That's pretty much what we care. And the main goal is to show that this nu x has to be an atom on some line. And we succeed on that, then we will be very happy. If we don't succeed on that, we will still will get something out of it. That's the main idea. So so the idea of what we are trying to do here is take a sequence Gn, any sequence, doesn't really matter, and as I'll remark, so we want to put some metric on the space X so that to make sense of this, we could do otherwise, but at the end of the day, essentially that's what we are doing. So we assume X is a compact metric space, and then we can discuss this convergence. Then we will take losing set of continuity of this measure nu, so that life is nice. Even if we wanted, I think we can make this to be a continuous action. We don't really need it because we can always go with losing sets of continuity, and that's all we care. Actually, if I'm not mistaken, the way you make it into a continuous action is by playing with losing sets of continuity, essentially. And then that's how you make it. But anyway, doesn't really matter. So we take this sequence there, and then we know that by appropriate choice of guys, this will be convergence to this business here. And on the other hand, we know that this is equal to this guy, and the whole point of this Furstenberg lemma is to discuss what happens when I have a sequence of matrices hitting a measure. What's the limit of this? So let me restate the lemma. It says let an be any sequence in SL to R, then either let me just do it this way. One, I may not be stating the same way as before. Okay, and let B equals all the equivalent statements are the same for me here, but I want to state at least one lemma. So assume oh boy, yes. Okay, I will assume we have convergence there to some matrix B, which is some 2 by 2 matrices. Then either 1 B belongs to GL to R, or 2 rank of B equals to 1, and there exists Ni going to infinity and E naught E1 in RP1, such that actually this should be the kernel of B and this should be the range of B, but the image of B, we don't really care. RP1 of ANI of L such that for every K contained in rp1 minus e naught supreme over k of this guy to e1 goes to 0, goes to infinity, and hence as a consequence, so what we really care is of the corollary of this. So this we discussed, we draw the picture, so we got quite convinced of this. So the corollary of this is that if nu is a probability measure on RP1, and here I should have written and norm of an, so sup in n of this is bounded, so this norm stays bounded, and this let's say lim inf of this goes to infinity, lim sup actually. The supreme of this is infinite. So just a way of saying I'm not in case 1. Then there exists ni going to infinity, and E3 in RP1 and C2, C1, oops, C2 in C2 in 0, 1, or in R, actually positive, C1 plus C2 equals to 1, such that A sub n star nu is convergent to C1 delta E1 plus C2 delta E2. Okay? So if I push any measure, no matter which measure, and I know that this sequence is going to infinity, actually a subsequence is going to infinity, then any measure is going to the combination of two deltas, maybe just one delta, larger than or equal to 0. So one of them may be 0, and hence the other is 1. Okay, let's prove the corollary. So let's take nubar as being nu minus E naught times delta of E naught, normalized so that it becomes also a probability measure. Really not important, the normalization, but I like to keep on working with probability measures. And the first thing we are going to show is that an goes, so ani, yeah, there should be a subsequence ani, so where is the very same guy as here, goes to star nubar delta E1. Okay, and so the proof of this, let phi continuous function, and we do phi on A and L, d nu bar of L, so that's the sequence we want to consider. So let phi sub n be equal to phi compose an. Oops. We have the subsequence here, ani, and we have that phi ni goes to 0, not to 0, I'm sorry, to phi of E1 nubar almost everywhere. So it's and actually this is true for, take the compact set K here equals to X, and as soon as K is not E naught, then this is true. And so the almost everywhere follows from the fact that nu bar of E naught is 0. And that's why I remove the E naught from there. So that this is 0, and then this almost everywhere is just the complement of E naught. Now the C0 norm is, the subnorm is actually the same as the subnorm of phi. So dominate convergence theorem tells me that this is convergent to the integral of phi E1, the nu bar, which is phi of E1. So if for every function I have this guy, so this is the integral of phi d ani star nu bar, if for every continuous function I get this limit, then it means by definition that this is the weak star limit of that. So that settles for the nu bar, and then when I do, so I have that nu is 1 minus nu of E naught times nu bar plus nu naught, nu E naught delta at E naught, and hence ani star nu, this is equal to 1 minus nu of E naught. So this is the C1 times ani star nu bar plus nu of E naught, this is the C2, times delta ani E naught. And this is convergent by taking a subsequence, so I assume nij of E naught to go to this direction E2. So this is convergent by the previous assumption to C1 delta E1 plus C2 delta E2. So this is C2. Now I have to take a subsequence to make this conversion. So that's the proof of the corollary, and I get is the union of the. So in higher dimensions, we have pretty much the same statement. You assume the supremum goes to infinity, and then you will have that the subsequence goes to a measure. So that's the trivial thing, having, because the space of measures is compact. But the point is that this limiting measure will be supported in the union of two subspaces. Okay? And each of these subspaces has dimension strictly smaller. And so that way I'm missing a lot of places in RP1. Or I have that the supremum stay bounded, and then we discuss from there. Okay, so now that we know this, corollary. let me see. So the corollary is as follows. It's actually a non-trivial corollary, but still. So there exists a set R, mu of R equals to 1, such that either one cardinality of the support of nu x is smaller than 2 for every x in R, or 2 for every xy in R, there exists a guy bxy. I need to say something else here. Okay, this will be true, but something else will be true as well. But let's start with this. Star nu x equals to nu I bxy here in SL. So 2, eventually to reach a complete proof, 2 will be expanded to more information. Okay, let's prove the corollary. So who is the set R? Set R essentially will be a set of continuity points for this map x into nu x, so it will be the disjoint union. So let L sub n mu of Ln go into 1, x into nu x restricted to Ln continuous. So for each fixed n, we can do that. Now take x naught. X naught will be a typical point any point actually is not really important, the choice of x naught, but it will satisfy some sort of Birkhoff ergodic theorem. So yeah, I don't want to talk about Follner sequences, but essentially the point x naught is so that you have a key distribution with respect to this x naught. So such that for, well, it will not be every point in Ln, so such that for every n there exists Ln hat mu of Ln hat equals to mu of Ln, so still going to infinity, Ln hat containing Ln, and such that for every y in Ln hat, and actually I could make it exactly the same because I could reduce a little bit the Ln hat. So, well, here it said nothing about Ln being compact. I typically want it to be compact. It's not so important actually, but I like losing sets to be compact. And then, well, here I could reduce Ln a little bit to have almost full measure inside Ln and being compact, and still the measure will go to 1. So I can rename all the guys. But anyway, there exists Gn in G such that Gnx goes to y, x naught. Okay. Now actually I should have done this a little bit better. Instead of starting saying who is R automatically, I should have first said that the set of point X satisfying this property is clearly an invariant set. So it's either full measure or zero measure. Okay? So I will assume it has zero measure and then show that the set of points satisfying this second will have full measure essentially. But other than that, it's not so serious. Okay, so here let's assume this is true. Okay, now I take this set R and I can further assume that all these losing sets are inside the complement of this guy. So this support has at least 3 points. So this sequence depends on the point y. So for every point x naught is fixed, will never move again. For every point y, I will have a sequence. So take y in R, cardinality of mu x strictly larger than 2, the support of mu x, of mu y, sorry, strictly larger than 2. And we know okay, the n here is not the same as the n there. It's a gk. So the first n is just okay. Now we know mu of y is the limit of mu gk x naught, which equals to the limit of phi gk x naught mu x. And since cardinality of the support of y, of mu y, is larger than 2, the norm of gkx naught stays bounded, and moreover there exists phi of gki x naught goes to some limit b. So the norm is bounded, so there is a limiting guy here, and b star. x equals to nu y. That's it. As trivial as that. There may be more than one b, so there may be several b's. Actually, that's the point. So this is for the x naught. This is x naught. So I fixed the x naught and I showed I could reach any y. Now if x and y, so let's call this bx not y. Now if x and y are in R, then, so this was true for every y in R. I had this business. Then I can write nu x as being bx not x star nu x naught, nu y is bx not y star nu x naught, and hence nu y is, I go and come back 4, no? So it's bx not y inverse times bx not, I guess this should be x, this should be y star nu x. And I'm done. Okay, what is important of this corollary? So in item 1, I have that the support is 2 points. Then I have 2 more cases. One where this support is just 1 point, the other where this support is actually 2 points. Always. Okay? Then in the second case, so, okay, now let's go back. Moreover, in the case the support is exactly 2 points always, I have the measure of each of the atoms. Okay? And then I will argue that, let me see if I'm doing it correctly. I will argue that either there is another invariant measure, and actually discuss some ergodicity of the measure nu to claim that the measure nu actually was not ergodic, or this measure that was supported on 2 atoms need to have both weight equals to 1/2. Okay, so this will be one statement. In either of the statements, the outcome is that these measures nu x are all essentially the same. So still, given 2 points, there is a matrix B mapping the measure nu x to the measure nu y. Because in the case of being just one atom, the matrix B, what it's doing is taking one guy to the other, and in the case of 2 atoms, I'm just taking these 2 points to any other 2 points. And linear maps are transitive in 2 points on RP1. 3 points not, but 2 points and 1 point it is. So in the third case, I still have that all measures look alike, nu x. Okay? And that's also what I will use. So the corollary of the corollary of the corollary is there exists a set R mu of R equal to 1 such that for every x, y in R, there exists bxy in SL2R such that bxy star mu x equals to 1. So this second property that I got in the previous corollary actually holds regardless of anything. So you always have it. Okay, so proof. So let R1 be the set of points x such that R2 It's x in R, of course. Now, by ergodicity, either 1 or R2 have full measure. Okay, of course I have the R3 is not equal to 3. So it's the rest. You cannot have empty support, so the cardinality is at least 1. So either one of these three sets has full measure. So if this guy has full measure, then we are done, because that was the previous corollary set. If this guy has full measure, then we are done, because this is all one-dimensional. Actually, if you remember where we start, we actually wanted this to be the case. And then we are fully done once this is the case. So let's go and see this case. So in this case, the claim is, so if mu of R2 is 2 is 1, then how do I write it down? So well, so I want to claim that the weights are exactly 1/2. Okay. Then both atoms in for mu x have the same weight. Okay, and actually what I define now is a set R hat. This is a claim, and the proof of the claim is you define R hat as being the set of points x, L, x in R2, and mu x of L strictly smaller than mu x of RP1 minus L. Positive, because if not, it's not fun. So is the set of atoms which has smaller measure than the larger atom. So again, by ergodicity, this set is invariant, because the guy that has small measure will still go to the small measure. So this measure will be preserved and this measure will be preserved, so the inequality will be preserved. So it's invariant, and then by ergodicity of nu now, because I took nu also to be ergodic, projecting into the mu that is ergodic, this is either full measure or zero measure. Now if this set is zero measure, then I'm done, because the complement of this set is exactly what the claim is asking for. There is no atom smaller than the other. Now, if this set has full measure, then we are in trouble, because where are these atoms? Are not seen in this set. Okay? So this measure cannot have full measure. Need to have measure strictly smaller than 1, because this set is only looking at the directions which has small weight. And there is no way a direction with large weight to belong to this guy. And the proof of this is just Rockling. Okay? I do nu of R hat is the integral, double integral of mu x of R hat and actually of the fiber, d mu of x. And now in the fiber, I can see only one of the guys, and I'm seeing the smaller one. So this guy is necessarily strictly smaller than 1/2. Instead of doing that, I could just put strictly smaller than 1/2 will be the precise same business. And so this is strictly smaller than 1/2, and so this total integral is smaller than 1/2. And then I'm done. And the point is that you are seeing only one atom, and you are not seeing both of the atoms. If you put the equal to 1/2, then you have two atoms, each measuring 1/2 when you do that. Okay, so this proves the corollary. So that's essentially yeah, I may need one extra. Let me think what I want to do now. Because we are almost done now. So let me do the easy statement. Then it's hard to prove, but it's easy as a statement. So in this corollary, actually, the way I will use it is by fixing one x and moving the y. Okay? And the claim is that I can make this choice here measurably. Okay? Now, why I can make this choice measurably is about sections. So let me discuss a little bit why I can make this choice here measurably.
Meaning choosing y measurably?
Choosing b of y measurably.
Okay, you fix the x
and then I can choose this matrix B of xy in a measurable way in terms of y. So if there was only one B of y, then it's almost obvious that it will have to be measurable. But since there may be several choices, then actually, once there are several choices, you can make it in a non-measurable way. So you can force it to make your choice non-measurable. And, well, we need a claim saying that you actually can make it measurable. Once I can make it measurable, I'm essentially done. So claim fix x in the corollary, in the previous corollary. Actually, what will be more important is the proof, not the statement, because the way you argue in higher dimensions is through the proof more than through the claim. Then y into can be chosen measurably. And the proof is actually quite simple once you get convinced of the following. I'm not sure I know how to get convinced, but it's quite obvious in reality. So is given x, okay, x naught is fixed, so given y, let s sub y, which depend on x naught, but x naught is fixed forever, be all the b's in SL2R such that b star mu x naught. So take all possible ones. So this is a subset of SL2R. And actually, I can take the space S, which is all the x y b's such that B belongs to Sy. And this is a subset of R times SL to R, which is actually a subset of X times SL to R. And the claim is that this set is measurable. And why this set is measurable is because nu of y is measurable. And this is the pre-image of the following evaluation function. So we take evaluation from X times SL to R into yeah, but I'm not sure whether I may want the probabilities. On RP1, yeah, I think I want to give the probabilities. And then to XB, I send it into, no, YB, I'm sorry. Well, Y, I keep the information, and then I do B nu X naught. Okay, so that's some sort of evaluation function. It's well defined, it's measurable. It's actually CR if you want to. So it's continuous in the second variable. So it's really a nice guy. And then, so it is measurable. And then what I'm taking is the preimage of the section, which is I, comma, nu of y. Okay, so I do F inverse of the set y, graph of nu. This is exactly yes. So I have this measurable set. And now I'm taking a measurable section of this set. That's it, that's all I'm taking. And that's always exists. So okay, now that I can do this, this is actually what I call, oh, wait a second. No, it's good, I don't care. That is what I call C of y. Yes. Okay. So remember that the whole statement says that I can make my cocycle cohomologous via a C of y measurable to a cocycle doing something. So let's conjugate by this C of y and see what happens. So
The C of y actually doesn't depend on X naught as well.
well, it depends on the choice. If you make different choice, you will just swap it a little bit, but not much of a difference. So actually, this is not the real C of y. I still need to make some extra adjustment for it to be the true C of y. But this will come later. So yeah, this is not C of y, this is a C hat of y. So yeah, let me not switch, but yeah, let C hat of y be V of X naught y less C hat of G y be, I hope I'm doing it correctly, notation, maybe nu hat of y star nu x naught is nu of y. So let's remember this. So then this compose times phi of gy times c of y, c hat of y. So clearly this is homologous to the previous one, and I will prove the theorem for psi hat. And the main observation is that psi hat of gy star nu x naught is nu x naught for every y. So what I did is I proved essentially Zimmer Amenable Reduction, but getting only that psi hat of g y or x stays in this set that I call is all the matrices A in SL2R, such that A star is equal to x naught. Now, if you remember how we started, well, it was not the complete start, but we made this discussion of what are these groups, this stabilizer of nu x naught. And this group is either SO, in the case that nu x naught is absolutely continuous. This group may be trivial, actually, in the case nu x naught is very singular type of measure. If this guy has one atom, this is upper triangular matrices. If this guy has two atoms of same weight, this group is this cross permuting guys. If this guy has more atoms which are distributed in the right way, this could be rotations by angle p over q, or whatever p, or 2 pi p over q, and that's it. That's all it can be. Okay? So, in the case of the rotations, you may put it inside SO. In the case of all the other cases, you get what you get. So in any event, let me restate the lemma, which we probably are going to prove on Friday, if we prove it, if I don't leave it as an exercise, which says that for every new probability of RP1, nu is either, okay, there exists an A, I'm sorry, or yeah, C in SL2R, such that C L nu C inverse is the same as L C nu, maybe C minus 1 star nu, is equal to either actually, let me make my life simpler. So either L mu C is equals to P equals to this A0 A inverse B plus minus, because I'm not insisting on positive determinant, so I have to allow this minus there, even though I don't like it. A in R minus 0, B in R, C. Okay, let me put a subset here and now my life is simpler, is contained in this permuting guy, which is this A inverse, and again, yeah, contained A different from 0, group generated by this union this, or 3 CL inverse C is contained in SO to R. And I'm not putting the equal, they can always be some sort of subgroup if you do things correctly, especially this third guy. I think these two guys, you need to have equality, but for this third guy, you may have strict containment. But in any event, this is a lemma about subgroup of SL2R. Okay?
So and what about this finite rotations?
This is a subgroup of this.
I see. Okay.
So yeah, I'm giving up equality, and then I have just this list of. And then I'm done, because then I pick this matrix C, which will bring this group into one of the three of the list, and then the final C of Y will be C hat of Y times C or C inverse. And then we are done. Let me add a couple of things. So there is other ways of ending faster, especially in this SL2, is just the claim that all these spaces are amenable, and then you are fine. So all these groups are amenable, all the new groups are amenable. That's an easy way of arguing. Now for higher dimension, the proof pretty much goes the same. So you just follow whatever I wrote, and you end up showing that your cocycle can be conjugated to one taking values in one of these L nu business. And then you argue inductively, essentially, or put some minimality conditions, where you want the support of nu to be the smallest possible dimension. Okay? So how you will measure it? Well, it will follow from what we are proving that you can force the measure nu to have its support inside the union of finitely many subspaces, or the projection into the projective space of finitely many subspaces. And then you want this to be in a minimal fashion. And you will argue that something like this is contained in something like this, and actually instead of doing this and using actually measures, you will do better by taking some families of subspaces, some other family of subspaces, and then this is certainly obvious. So this means the set of matrices preserving this family of subspaces. So F1 is some union of subspaces, it's a finite union of subspaces. So is some E1, EK1, EI in RD subspace. And actually you care, so this LF1 will be the A's in SLDR such that A of the union of the AI's is equal to the union of just this. So this is a subgroup which satisfies clearly this property here. And then you argue some sort of maximality type of assumption, or minimality type of assumption. And our main lemma essentially will claim always that you can reduce to a guy preserving the measure. This L nu will be a subgroup of one of these guys. Pretty much the same as we are doing here. And that's almost it, so there is not much more you need to do at the end of the day. Okay. Whew. Yeah, it's time. So this is the end for amenable reduction. I may discuss a little bit more on Friday. If not, I probably start stating Zimmer cocycle super-rigidity. We'll see if we can make the proof of Zimmer cocycle super-rigidity. Okay, very good. See ya. So today what I'm going to do is to just go easy and prove the classification of these groups L nu. So let me remind you what is this guys L nu. So given a measure L nu, oops, a measure nu, probability measure on RP1, we define L nu as being all the A's such that A star nu exists. Now there are a couple of observations here. So one is that if A is in L nu, then minus A is also in L nu, because the action into the projective actually goes through what is called PSL to R, which is PSL mod plus minus identity. So that's the projectivized version. So I always have to put a plus minus in whatever we do. The second thing is that, as we have seen, there are three main cases of this L nu which are really the relevant, and let me list them. Is the first case is when nu is delta at 1, 0, in which case L nu is upper triangular matrices. The second important case is nu equal to 1/2 delta 1, 0 plus 1/2 delta 0, 1. And this case, we have that L nu is the map preserving the cross matrices preserving the cross. And the third case is here. Is SO 1, in which case nu is Lebesgue measure. So these are the three main cases, and the claim is that no matter which is the measure, you will be conjugated to one of these three cases. So I want to give now a description of these three cases, which are independent of measures, because that free me a little bit of these measures. So case 1 corresponds to LF. So let me maybe define, given F in R2, we define, well, actually I don't even need to be a subspace. I can just define, of course, I will only use it when it is a subspace. So define L sub F A in S to R such that A of A, oops, A of And since this guy, well, as I said, I typically will care about subspaces F, so there is an RP1 version of it using subspace subsets of RP1, and you can imagine what is the relation between one and the other. Okay, so the property then is that in the case 1, you have L nu is L10, which this thought as a direction 10. The case 2I, we get L nu is L10 union 0, 1. So we preserve these two spaces. And the case 3 is a different case, so the case 3 is SO2R. Okay, you preserve a metric. So I could give a characterization of this as the guy that when you act on the space of metrics or things like that, you have a fixed point, things like that, but I don't want to do it. So that's good enough, because this is a really, you have to think of this as a special type of guy. It doesn't mean it doesn't appear, it shows up quite frequently, but it's different from preserving flux. So the typical operation when you play with matrices and with cocycles is you look for the splittings. You look for the invariant bundles. When you stop finding invariant bundles, you should get into this SO. Okay? So restricted to a bundle which has no invariant subbundles, you have to be orthogonal. Times R, of course, because this is only projective picture. So that's our theorem, or lemma.
So we just not care about this finite rotation case because it's like finite. It's a finite group.
Because it's a subgroup of this, and we are happy with that. And that's what the lemma will say. So for every new probability measure on RP1, either 1 L nu is, oh, I forgot to say that. Well, there exists a C in SL2R such that L nu is inside Z L10 inverse, or C L sub 10 union 0, 1 C inverse, or L nu is a subgroup SO2R Z inverse. So you are conjugate to belong to one of these three guys. Okay, you could be much smaller, so you could be diagonal, because if you take the nu, for example, the measure supported on the 1, 0 and the 0, 1, but without equal weights, then you will be diagonal. But still you are inside upper triangular. Here, I don't think you, well, here you have diagonals as well, so you could be here as well for the diagonal. And inside here, you could be a finite rotation, a rational rotation, and then you will be here, and the measure nu will be different, but still you will be here. Okay? But still you are conjugate to one of these situations.
So in the rational rotation case, they can have delta, not Lebesgue, right?
You have, so you can start with delta, but you will be a subgroup of the guy having Lebesgue. That's a good example. So if I take nu equals to sum 1 over q delta e to the 2 pi iq j over q from j equals to 0 to q inverse, and I have to be careful because it's projective. So let's say q is odd. I guess if q is odd, I'm fine. if Q is even, then I have the minus. No, I always have the minus. So it has to be twice, I guess. Anyway. No, I don't need to do twice. So if they are counted twice, they are counted twice. I don't care. So it's still a good probability measure on the space. Let's say Q at least 3 to maybe 10. And then I get that L nu is inside L lambda, which is SO. Is a strict containment because L nu is exactly the rotations, the groups generated by these rotations by angle 1 over q, 2 pi 1 over q, but is a matrix in SO. So I can put it inside there. So let me characterize actually better these three main bundles. Actually, let me get rid of this existence of the matrix C. So let me go back to case Li. So this is Lf, where F is a one-dimensional space. Case 2 is where F1 plus F2 is R2, and case 3 is matrices preserving an inner product. Some inner product. May not be the Euclidean, any inner product will do. This is conjugate to S2, SO2. And that's exactly what we are going to show. That any L nu either preserve, all the matrices preserve the same linear space, or preserve the same union of two linear spaces, or preserve an inner product. And actually, the main work behind that was already done. Proof of lemma. So I consider this norm with respect to the Euclidean metric from L nu into R. Okay, it's this function. And then we have two cases. Either this guy is unbounded, or is bounded. It's a bounded function or an unbounded function. It is continuous, I don't care, but it's either bounded or unbounded. Now, if one, then support of nu is less than 2. And that we saw last time in this Furstenberg lemma. Because we will have that an star nu converge to nu, because it's always nu. But we know that this, given any measure, if the norm of an goes to infinity, then this limit is the combination of two deltas, which may be the same delta, or maybe one of the constant is smaller. And so if this is unbounded, I will have a sequence of matrices whose norm goes to infinity, and so this will go into nu, because this is always nu. and this will have to be the combination of two. And in the second case, what we are getting is that L nu is compact. Well, I should say why it's compact. It is closed, okay, because the fact of preserving the measure is a closed condition and is bounded as a subgroup of, as a subset of R to the 4, which is 2 by 2 matrices, and so is compact because the topology on SL2R is the inherited topology from being a subset of R to the 4. And so if it is compact in R to the 4, it's compact in SL2R. And so if it is, and it's compact because it's bounded. So closed and bounded is compact. So it is a group if it is a compact group. So let's finish in item 1. So in item 1, I have either the support of nu is 1, in which case it will support on a line F. So in this case, nu is delta at F, which implies L nu is inside LF. In the second case, I get nu is C1 delta F1 plus C2 delta F2, and in this case, we can easily check that L nu is contained on L F1 union F2, and we are done. And then in the last case, I get the group is compact. And now I have to show that the compact group is conjugate to SO. So let's do it. So let M be hard measure on L nu. Since L nu is compact, M of L nu is finite, and we can normalize. Well, I don't need to normalize. Then I will define an inner product. So define as being 1 over, actually I don't need to normalize, either is the integral of AB AW d M of A. Let's just integrate it. Okay, so then 1, this is integral of, okay, sorry because I'm using the same notation here. So for dot is a standard Euclidean product, this is our nu. Maybe allow me to call it L nu, because after all depends on this L nu. So this is the norm of EAB squared, the M of A, and this is positive. So it is a positive product. Also, if it is 0, then norm of AB squared is 0, A almost everywhere, which implies, just pick any of these A, implies A of B for some A, well, actually, imply A of B equals to 0, which implies B equals to 0. Because matrices A are invertible in SL2R. So we get positivity. It is linear because it's trivially linear in both coordinates. It's symmetric, anti-symmetric, depending on, well, we are in reals here, so It is symmetric, so it's an inner product. And finally, if I do B of B, with B of W, this is the integral of A B of B dot A B of W dm of A, and this is equal, and now I use invariance of the measure with respect to translations. That's the whole point of our measure, which is invariant by, in this case I'm using invariant by right translation, but this compact, so it's by invariant by left and right translation. So this is integral over L nu of A B dot A W d m of A, which is BW. So this is true for every B in L. So any matrix in L preserve this inner product. That's it. Now, why matrices preserving an inner product correspond to SO is because any inner product is the same as a standard Euclidean product. So you take C such that C take this matrix C doing that, and that's conjugating this inner product to that inner product. And then why this matrix exists? Because this is a positive definite bilinear form, and any positive definite bilinear form is conjugate to the standard linear. Okay, so that's settle all L news. Now let me go back and discuss epsilon higher dimensions. So the arguments we did, in a sense, works always. Okay, so let me go back to this lemma by Furstenberg, but now in any dimension. So I take an in SO d R, any sequence, not in SO, but in SL, I'm sorry. So it's any sequence, and take nu a measure in RPD minus 1. Okay, the projective space of one-dimensional space is there. Then either 1 the supremum over n of norm of an is finite, or 2I there exist measures nu1, nu2, probability measures C1, C2 positive, C1 plus C2 equals to 1, and subsequence Ni such that Ani over norm of Ani. Well, actually, I don't need to. So this is part of the proof, so I don't need to write it here. So I have these probabilities, and but spaces F1 subspaces such that dimension of F1 plus dimension of F2 equals to D. Doesn't mean this is a direct sum. They could even coincide in principle, but still you will have that dimensions will match. So that's support of nu I is inside of these directions in RPD minus 1 such that L is inside the Fi. So it's this shadow of these spaces in this RPD minus 1. And finally, you have that there exists Ni going to infinity such that Ani star nu goes to C1 nu1 plus C2 nu2. So you have subbundles. So in particular, the support of this limiting measure is not everything. Okay, because this set here is a small dimensional manifold inside this projective space. Well, I should have said, I'm saying this, and also dimensions, dimension of F1, 1 second, of both guys are strictly positive, so larger than or equal to 1. So, yeah, because if F1 is everything, then there is not much fun there. So, you want both spaces to be, actually what is important is not that, but this plus this gives you the consequence, is that this is dimensions smaller than D minus 1. But anyway. Still remember that either of these guys could be 0, so I'm not saying both spaces are really appearing, but at least one of them is appearing.
So if we allow the full Grassmannian, could we have arranged nu i's and fi so that the convex sum of the support equals fi? Because here you're catching the support, but you may still have like lots of.
I agree. So this is, you're right. So this is the key lemma. Then over this key lemma, you have to build some sort of induction that you could do in the Grassmannian, or you could actually do already still in the RD. So I agree with you. What you would like at the end of the day is to have some optimal description as we would have, hopefully, in this two-dimensional situation. But the sad news is that no, you cannot do that. And even in SL2, you face this sad situation, because these are very bad guys. But you see, imagine you have this group of rotations, okay? And now you take a fundamental domain and then put whatever measure you want here. Just think of whatever you want. And then you copy it here, 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 by the rotation. And then you do the average of this copying, so you just take the measure, which is that, and then you consider L nu. And this will give exactly, so unless you do essentially putting Lebesgue here, which will be the only strange case, so if you do anything else, then you still will have only the rotations by angle 1 over q, or I over q, and nothing else. And so what is the measure? The measure could be whatever it is. It is true that this is a situation which is in this first guy. So in this supremum of the norm being finite. Not in the case you are going to infinity, but this is because this is 2 dimension. You could have, let's say, in dimension 3, you have a here and there, and then inside here you have these rotations multiplied by some numbers, lambda, and these lambdas are allowed to be large. And here you have just one other number, which has to be 1 over lambda squared. because you want determinant 1. So then in this case, you will get essentially this splitting, that this line is preserved, this line is preserved, or not this line, this two-dimensional space, but the measure inside this two-dimensional space could be as bad as this. The norm still goes to infinity. So you cannot really have this finer description of the, so optimal finer description of the measure. But still, you essentially should be able to do what you want. And that's why you have this, Zimmer Amenable Reduction, which is what I said before. So you stop splitting the bundles when you get into SO. Then when you get into SO, you have no clue what is the measure. So that's how much finer you get. So the support of the measure will span a subspace, and your matrix will have to be conformal on this subspace. That's pretty much the idea. Again, it's just an idea, because here we are having just a sequence of matrices. So as soon as these sequence of matrices are asymptotically like one of the ones we were describing, you will have this phenomena on the limit. Okay, so in the application, we are not taking any measure, we are taking measures which are invariant by these matrices or things of this sort. So you're getting more information. So, but it's a very flexible lemma, which allows you a lot of things. So yeah, certainly when you want to recover Zimmer Amenable Reduction, you want to really explore this lemma a lot. And so far what this is telling us is that your L nu is inside SO, because in this case, the very same proof will give you that up to conjugacy you are inside SO, or you stay here, preserving these two planes. And then you go back again. Okay? You split your measure, you divide your guys, you take a finite index subgroup or whatever. You take LF1, LF2, take quotient spaces, and you restrict to the guys preserving this, restrict to the guys preserving this, and then you have the permutation. But the permutations are just finite permutations, so you don't need to care. And then inside here, you apply it again, so you split again, and some induction tells you have a finer splitting, where on this finer splitting, you land always into this property. So that's pretty much. And this is the classification of this amenable reduction, the way I wrote it. Or I'm not sure I wrote it, but anyway. I think there was one more thing I wanted to say. Okay, no, I'm not remembering. So this is a very standard group. So that's always with compact group actions. So all compact group actions are isometric. And that's the proof. So as soon as you act on a space that makes sense, you are isometric. Okay, let's say you have a compact group action on a compact metric space. Then you define the same. So you have G compact, G acting on X, where X is compact metric. Actually, it doesn't matter, X is compact metric. It's totally this metric. Then you define the matrix D bar XY as being the integral of dgx gy over triangle inequality is trivial, positivity is the same as we have done, and the group property will give you that you preserve this distance. And the fact that this distance is equivalent to the previous distance, again, is the group property. Maybe you want to assume some. So the fact that it defines the same topology is not so bad. If you have on top of it that they are Lipschitz, then they will be Lipschitz conjugate equivalent. If not, no. So yeah, so this is a general situation. So compact group always act isometrically. So that's a matter of fact, which is important. Okay, so let me not start. Let's finish early today, and yeah, I hope on Monday to start discussing this Zimmer cocycle super-rigidity. So at least to state it and say a little bit of what it's telling us. Okay, that's it for today. Thank you. See you next week. Bye-bye.